Science has become a dominant force in modern society. Discoveries made by scientists have reshaped how we look at the world and have led to technological breakthroughs that have put men and women in space, cured deadly diseases, and made life easier for millions of people. Underlying many scientific discoveries are common procedures people use to make sense of their surroundings in daily life. In this program, we will present a procedure called the scientific method. How are we to know if something we hear about nature is true? Some people are saying that the Earth's climate is changing, getting warmer, and if this warming is actually happening, will the weather become more extreme? For instance, will there be more droughts, hurricanes, and tornadoes? And will these extreme events become more intense? Other people say the climate is actually cooling. How are we to know the truth about these matters?
Over time, people have developed an outstanding procedure for uncovering the secrets of nature. It is called the scientific method. The reason the scientific method is outstanding is that when you use its 5 steps to solve a problem, this procedure can be repeated by anyone to check out firsthand the truth of someone else's results or conclusions. It's sort of like that one time when I heard that white light was a blend of many colors. Hard to believe that white light is actually a blend of many colors, right? But with the use of a simple tool like a glass prism, anyone can discover the rainbow of different colors by passing light through this piece of glass. Using the prism here to show what light is made of is a relatively simple experiment, and experiments are all part of the scientific method. An example like that is why I don't have to take it on faith or believe it because some very well-known person said he or she knew that the facts were true. The scientific method is like that.
In fact, experiments are an everyday part of science and the cornerstone of the scientific method. Let's look in a general way at the steps that make up the scientific method. Step 1. Ask a question.
As you can see, I'm drinking hot chocolate from this cup, and the cup is made out of a ceramic material. As you all know, hot drinks are also served in paper and styrofoam containers. Now I wonder, which of these 3 types of materials will keep my hot chocolate drink hot the longest?
Step 2. Form a hypothesis. Alana has noticed most coffee shops serve hot drinks in paper cups. So could it be reasonable to assume that paper is the best insulator? That is, it should do the best job of keeping the coffee hot. Now Alana believes she's ready to make a hypothesis, a prediction. The paper will hold the heat in longer because it is a better insulating material. In a sense, she has made an educated guess as to what is going to happen. So what is her next step? Step 3. Design and conduct an experiment. How can Alana find out what really is the truth about the materials that make up these containers? One way is to design an experiment which will actually demonstrate to Alana which container has the best insulating material. Suppose she puts the 3 types of containers side by side, heats up some water, and pours equal amounts of the hot water into each of the containers. It would be good to measure and record the temperature in each container at the very beginning to verify they are all the same. Then she would record the temperature again 5 minutes later and repeat this procedure until 20 minutes has passed. She would write down the measured temperatures for each kind of container at the 5-minute interval. At the end of the 20 minutes, the experiment would be completed. Step 4. Analyze the results of the experiment. Here is a graph plotting the temperature change for each container. We can see after 20 minutes, the temperature in the ceramic mug was 110 degrees Fahrenheit or 43.34 degrees Celsius. The paper 112 degrees Fahrenheit, or 44.44 degrees Celsius, and the styrofoam retained the heat the best at 120 degrees Fahrenheit, or 48.89 degrees Celsius. So, Alana's prediction that the paper would be the best insulator turned out to be rejected. Perhaps there are other reasons paper is used more often in coffee shops. Paper may be cheaper or more recyclable. Step 5. Draw a conclusion. Based on our observation, styrofoam is the best insulator for keeping the hot chocolate hot the longest. In addition, the whole procedure may raise some new questions. Why is styrofoam a better insulator? Or if the paper were thicker, would the results have been different? One way to look at the basic steps used in the scientific method is to divide them up into 3 stages: pre-experimental stage, experimental stage, and post-experimental stage.
Over time, people have wondered about many things and asked many questions about the world around them. Why is the sky blue? Where does rain come from? Where did I leave my wallet? Well, people haven't just wondered and asked questions. They've tried to answer their questions using something called a hypothesis. That is to say, people would form an educated guess as to what the cause of a problem they were experiencing was, and then they'd perform experiments to see if their guess was correct. For instance, I have these silver objects. You'll notice they're tarnished. My question is, why do bright silver objects become a dull gray tarnish over time? I wonder if it's anything like when a nail becomes rusty. My hypothesis is that perhaps the silver in this object reacts with oxygen in the air, much in the way that the iron in a nail reacts with the oxygen in the air to form rust.
So Sam noticed that silver tarnishes, and he was curious to know why this happens. He then formed a hypothesis that if silver is exposed to oxygen, then tarnish will develop. These are the first 2 steps in the scientific method: 1, finding a question, and 2, forming a hypothesis. Let's look at some different questions and see what hypotheses might be proposed to answer them. Had you ever wondered why archaeologists are always digging up ancient ruins? Did these ruins actually sink by some force of nature, or might it be that they're covered up? And have you ever noticed that worms come out after a rainstorm during the night? Why? We might guess that it's because they were drowning. Or another hypothesis might be that they come out to mate.
The number of questions that can be selected to launch the arduous and glorious journey down the road of the scientific method is endless. And once a question has been selected, such as where did this candlestick come from and why is it tarnished, there are many hypotheses that can be offered to explain the phenomenon.
Finally, formulating a new hypothesis can impact our lives in a variety of ways. For instance, when Albert Einstein formed the hypothesis that light was made up of particles, scientists knew that if this hypothesis were true, the consequences would change our understanding of how light behaves. After completing the first stage in the scientific method, finding a question, and then formulating your hypothesis or prediction, it is time to enter the experimental stage of the scientific method. While experiments can look very different, the following parts are essential elements of any experiment. Number 1. Gather materials. This procedure can be as simple as finding a piece of paper and pencil, or finding equipment as complex as a high-speed computer with vast amounts of memory. Number 2. Know how to use a piece of equipment. Sometimes in doing your experiment, you'll have to learn how to use a tool, such as a graduated cylinder or stopwatch. Number 3. Observe and record data. Obviously, a record of the experiment must be kept, whether it's done with a pencil and paper or video camera. Remember, the importance of the scientific method is that the experiment can be done again by other scientists. It must be repeatable. Number 4. Identify a single test variable and control other variables so only one condition is being tested. This procedure is at the heart of every experiment. For example, the test variable here is the distance of a light meter from the light source. As we can see, light intensity increases as we approach the light. Number 5. Perform measurements. Many experiments will require taking measurements. This may involve timing with a stopwatch, measuring distances with a meter stick, reading temperatures on a thermometer. Number 6, use mathematics. When carrying out some experiments, it's necessary to use mathematics. For example, if records were kept for a week, division would be needed to find the daily average of the number of birds found in a half acre of wetlands. Generally, in every experiment using the scientific method, you find some combination of the above 6 procedures. Now let's look at 2 experiments and see how the preceding 6 components of the experiment play a role in each experiment.
I have noticed at night ants do not seem to be active in the out of doors, while during the daytime I have seen them traveling over the ground. Scientists often have curiosities about the behavior of a certain animal species. My question is this: how does the level of ant activity outside of an ant-hole change from sunrise to sunset? I propose this hypothesis. If the temperature of the air is the warmest, then the greatest number of ants will be observed at that time of day. What I have here is an ant-hole in between 2 slabs of concrete. What we can do is count the number of ants that come out of the hole for a period of 1 minute at the beginning of each hour, starting at 8 in the morning and stopping at 8 in the evening. Also, the temperature will be taken each time the ants are counted.
When I water this yard, I hope the water will sink into the soil, not just run off. What's the best kind of material for absorbing water? My hypothesis is that dark organic soil will absorb the best.
Let's do an experiment to determine which kind of soil is best for absorbing water. Here are 3 different kinds of soil: packaged organic rich soil, packaged fine sand, and packaged coarse gravel. They each have a different kind of texture. They may feel smooth or coarse or even spongy to the touch. Take these coffee filters and place one in each funnel. Then place 200 milliliters of material from each by volume in the coffee filters. Position the funnel in a graduated cylinder. Then pour 100 milliliters of water onto each material. After 5 minutes, collect the water that has not been absorbed. Let's examine and compare the previous 2 experiments and see how the different parts of the experimental stage were used. Gathering materials. In experiment 1, the materials needed were an ant hole, ants, paper, pencil, a clock, and a thermometer. In experiment 2, we needed 3 different types of material: coffee filters, funnels, graduated cylinder, a tool to measure volume, a clock, and a pen and paper to record the results. Learning how to use a piece of equipment. Neither experiment uses complex equipment, only simple measuring instruments. Observe and record data. In experiment 1, the ants emerging from the hole were simply counted and the temperature measured, then the results written down on a piece of paper. In experiment 2, the results from the measurement of the water's volume, which had not been absorbed by the different soils, were recorded. Identify a single test variable and control the other variables. The test variable in experiment number 1 is the air temperature. In experiment number 2, the kind of soil is the test variable. Perform measurements. The only measurement in the first experiment was to use a clock and thermometer to determine the top of each hour. In the second experiment, we needed to measure the volume 3 times. First, the volume of material. Secondly, the volume of the water poured onto the soil samples. And finally, the volume of the water not absorbed. Use mathematics. The first experiment employed counting and timing, while in the second one, we chose to compare volumes of water absorbed by each type of material expressed as an equation. The initial volume of water poured, 100 milliliters, minus the volume of water collected in the cylinder, 88 milliliters, equals the volume of water absorbed, 12 milliliters. We've seen that while each experiment is unique, both experiments shared a common set of elements. Analyze results and draw conclusions. In performing the scientific method, once the experiment is completed, it's time for the post-experiment steps of analyzing the results of the experiment and drawing conclusions. In the experiment to determine which kind of soil, sandy, organic, or gravelly, is best for absorbing water, it was found that organic soil most readily passed water through it. At the beginning of the experiment, the hypothesis was that the organic soil would be the best absorber of water. The question now was, why did the organic soil pass the water most readily? The answer was found when we learned that the organic soil contained large amounts of mica, a mineral that was put in the soil for the purpose of draining water. Louisa found out that in the spring, when she conducted the experiment, her hypothesis was not true. In the first graph, we can see ant activity plotted against time. We see that the ant activity remained about the same until the sun started going down, and then activity increased. In graph 2, temperature is added, and we can now see that temperature is not affecting ant activity as much as time of day. In these final 2 steps of the scientific method, we try to explain and understand why the hypotheses were not confirmed. In the soil experiment, we had to learn about soil content in order to understand and explain our results. In the ant experiment, we found that during the spring, time of day was the determining factor as an indicator of ant activity, not temperature. Explaining or finding the cause of the experimental results is the most important part of the scientific method. Now that we've seen the 6 parts of the experimental stage of the scientific method, let's follow Kira as she conducts an experiment.
Let's suppose I walk around this kitchen and see what I can discover by just touching different objects. Some objects feel warmer than others, and then there are ones that actually feel cold to the touch. It seems the warmer ones are cloth or plastic, and the colder ones are metal. Stone and glass seem neither warm nor cold. These observations could then lead to the question, why do some objects feel warmer than others? I could then make the hypothesis predicting that if I were to place an ice cube on the surface of each material, the items that felt the warmest would melt the ice the fastest.
In order to test this hypothesis, Kira needs to get an object that is made of each of the following materials: aluminum, wood, and styrofoam.
Warmest, middle, and coldest.
All of the objects tested should have a flat surface and the same amount of mass. She also needs ice cubes of the same size. In the experiment, place an ice cube on each surface and then observe which one melts the fastest. Remember the prediction? Since the styrofoam feels the warmest, the ice cube sitting on it should melt the fastest. But to Kira's surprise, the result of the experiment is just the opposite of what was expected. The ice cube on the aluminum melted the fastest, and the ice that lasted the longest was on styrofoam, which had felt the warmest. So let us analyze the results of this experiment. Maybe when a material feels cold to our hand, it is actually losing heat to it. When the experiment was started, she did not consider that the materials tested were the same temperatures as the room, and the temperature of her hand was much warmer than the materials or the room. The styrofoam felt warmer than the other materials because there is very little matter in it, mostly very small air pockets, and when she touched it, her hand did not lose any heat to it. But when her hand touched the more compact and solid aluminum, heat left her hand and went into the metal. Her hand actually was cooled because of this. Because the materials tested had the same temperature of the room, what she experienced were different amounts of energy loss.
Was I wrong?
The scientific method is important because it provides a procedure to test anyone's experimental results. People no longer have to rely on someone's authority, since they can perform the same experiment and observe if they get the same results and draw the same conclusion. We have also seen that the scientific method forces the experimenter to explain and ask why he or she obtained their results. In this way, science continually advances by the asking of new questions. Scientific Method Video Quiz. True or false? The 5 steps in the scientific method are: ask a question. Form a hypothesis. Design and conduct an experiment. Analyze the results of the experiment and draw a conclusion. True or false? Observing and recording data are part of the experimental stage. True or false? Many experiments will require taking measurements. True or false? Scientists' answers to the world come in part from what they observe. True or false? If more than one variable changes in an experiment, the outcome will remain the same.